In this video, we're going to do the heavy lifting that will help us justify our reasoning for Kosaraju's algorithm. And it's going to start with a pretty bold claim. If I order the strongly connected components in descending order of the highest post number in that SCC, this is a topological ordering of the SCCs. Again, we're kind of assuming in this case that we already know what the SCCs are, and we're going to get rid of that assumption soon, I promise. But for right now, let's say I already know what the SCCs are, and I want a topological ordering of them. Maybe you can think of it as a topological ordering of this DAG that we drew earlier for the metagraph, because the metagraph is a DAG of the strongly connected components. So, if we want to find that topological ordering, we just need to find the highest post number in each SCC and then reverse that order. Basically go from the one with the highest post order, then the next highest post number, then the next highest post number, etc., etc., etc. So now's a good time to just kind of remind ourselves, what does it actually mean to have a topological ordering? What it means is that if there's an edge UV, and I'm just using capitals here because they're components instead of just normal vertices, so, so if there's an edge UV, then U comes before V in the ordering. So let's take that a little bit further. So let's say this is a topological component C1, and here's its vertex U with the highest post order. Here's another one, C2, has a vertex V with highest post order. What we're saying is if there's an edge from U to V, or not from U to V, but from C1 to C2, then C1 has to come before C2 in this ordering. What does that mean? That means that the post number of U would have to be greater than the post number of V. That's what it would mean in this case for C1 to be before C2 in that topological ordering. So, what we can say is if there is an edge, all we need to show that this is a topological ordering is if there is an edge from C1 to C2, then the highest post order, or the highest post number, I'm going to say post order instead of post number this entire video, so I just apologize in advance. The highest post number in C1 is greater than the highest post number in C2. Okay, so first, I have this picture here, and this picture is really going to help us justify this claim. And this is going to be, even though I promised we're going to justify this, this is going to be a kind of sketchy justification, but I think that you'll follow along. And I think that you'll agree that this does enough of the job. So first, I'm going to note that if there's an edge from C1 to C2, and these are each strongly connected components, there can't really be any path even from C2 to C1. Because if there was, then I'd have a way to get from everything to in C1 to C2, and then I'd also have a way to get back to C1, and they'd actually just be one single strongly connected component. So what we can say for sure is that there is an edge from C1 to C2, but there's no path even from C2 to C1. So what we're going to do is we're going to basically look at this as I can either explore C1 first or explore C2 first. And what I mean by that is, so I either have to, as I'm doing my, depth first search, I'm either going to have a vertex in C1 show up before a vertex in C2, or I'm going to have a vertex in C2 show up before a vertex in C1. So let's break up into those cases. So let's say I encounter C1 before C2. Since there's an edge from C1 to C2, I will finish. Remember, there's like this stack structure here. As soon as I find an edge, I'm going to take that edge and then go explore some other stuff. So as soon as as I'm going through here, I'm going to process C2 all of C2 before I complete processing C1. So, how you could think about it is I'm exploring C1, and eventually I hit the vertex that's actually adjacent to something in C2. So as soon as I hit that vertex, at some point, I'm going to take that edge and then go start in exploring C2. Since C2 is a strongly connected component, I'm going to, explore everything in that, maybe explore some other stuff. But what I'm not going to do is I'm not going to go back to any vertices back in C1 because there's no paths from C2 back to C1. So I'm going to explore a bunch of stuff in C2, maybe some other stuff, but I'm going to be done exploring C2 and, give my final post number to something in C2 before I kind of backtrack and finish processing the rest of C1. Because remember, consider that vertex that took me to C2. I haven't assigned it a post number yet because I haven't come back to it. I haven't finished processing all of its edges. I still need to do this edge and then everything in C2. So we started in C1. At some point we took a trip over to C2. We do everything I can get to from C2, finish C2, and then we eventually backtrack and then finish processing C1. What does that mean? Well, I finished processing C2. I assigned the last post number I could in C2 before I assigned the last post number in C1. So this means, and again, I'm going to use U as the vertex with the highest post number in C1, V as the highest post number in C2. This means that post of U is greater than post of V. So that's what happens if I start with C1. But what if I start with C2? What if I start with C2? Well, then let's think about what happens. I'll get to C2, I'll explore everything I can from C2, but that does not include C1 because there's no path from C2 to C1. There's no path from C2 to C1. So I finish processing C2 before I even start processing C1. Ew, I can spell words. I finish processing C2 before I start processing C1. Thus, I'm going to assign the highest post number to that I will in C2 before I assign the highest post number in C1. So we still see that post of U is still bigger than post of E. And those are the only two things that can happen. Either I encounter C1 before C2 or I encounter C2 before C1. So it works. Okay. So with this, we have justified that if I order the SCCs in descending order of the highest number in that SCC, this is a topological ordering of the SCCs. And there's a big consequence of this, and a kind of more subtle consequence. The first big thing is that the vertex with the highest post number must be in a source SCC, because it's going to be the first in this topological ordering, and the first thing in a topological ordering is going to be a source. What that means also is, if I delete or maybe ignore all the vertices in previous SCCs, the remaining vertex with the highest post number is in a source of the remaining in a source of the SCC of the remaining graph. I'll scroll down a little bit. Okay, that line's just going to be there for a bit. Okay, it's going to be a source SCC of the remaining graph. Please turn back to black. Okay, and this is kind of crazy because I don't need to know what the SCCs are for this to be true. As long as I know what the highest post number is, I can tell that that vertex belongs to a source SCC. And again, that doesn't involve me knowing what the SCCs are in advance. That just involves me knowing what a post order is, or what the post ordering is in advance, which I can find nicely in linear time. That's great. This second comment kind of has something to do with the SCCs, but I promise that's going to not be a problem, because essentially the first thing is going to help us find an SCC. And as you're thinking, you might be noticing, wait a second, you just wrote source a bunch of times, but if I recall last up here, you wanted to find a sync SCC. So what's this all about? Why are we finding sources instead of sinks? Well, the reason why we're finding sources instead of sinks is because we actually can find sources. It's kind of hard to find sinks. So then the follow-up question is, what does finding a source have to do with answering this problem? And that's what we're going to answer in the next video.